we consider the third example. The third example, f is a continuously differentiable function over the closed unit ball. That is the closure of the closed ball. And also f is zero. F is zero on the boundary of the ball. So this is the situation. We have a unit ball, and f is zero on the boundary. And we are required to compute this limit. I is the limit as epsilon goes to zero, epsilon positive, over the region. Maybe I should epsilon x gradient of f x over the norm of x to the power m. M is the dimension of the space. Then dx. So this is an integral, m triple integral, n-fold integral, integral in m-dimensional space. So how to do this? So this is the ball, and this is epsilon. So this integral is over this region, bounded by these two spheres. This is the integral domain of this integral we want to compute. So how to compute this integral? Consider this integral. X gradient of f(x) xm. So we have the inner product of x with the gradient of f. So this makes us remember the first Green identity. The first Green identity tells us that gradient of u, gradient of maybe gradient of v. Okay, u plus u Laplacian of v. This will equal over the boundary u and right. The right hand side is the divergence of u. Okay, so applying the divergence theorem, we have the applying the divergence theorem to the vector function f equal u gradient of v. We will obtain that this is just the first Green identity. So compare the first Green identity with our result. We already have a gradient of f. So we want to find a function. Find a function v such that the gradient of this v, the gradient of this v is xm, and the Laplacian of v will be simple, as simple as the simpler the better. Maybe it is 0. Can we have such a function? The gradient is x divided by the n power of the norm of x. Can we have such a function v? Yes, there are some such function. We take the v, let v be the function x to the power n minus 2. That is x 2 minus m. So we compute this v. The partial derivative of this v by the chain rule is 2 minus m x. 2 minus m minus 1, that is 1 minus m. Then partial derivative of the norm of x. And we know that the partial derivative of a norm is just xi over the norm. Okay, so using this result, we can continue this computation to get 2 minus m x 1 minus m, then xi norm of x. Then this is 2 minus m x norm of x minus m, then xi. Okay, so we can compute the second derivative with respect to xi. That is 2 minus m partial derivative of norm of x minus m xi. Then applying the Leibniz law, we will obtain 2 minus m x2 minus m plus 2 minus m xi, then the partial derivative of x minus m. Okay, this is the multiplication of two functions, and we want to compute the partial derivative. So each time you differentiate with one function and then multiply the other, then some other result you obtain the deserved result. That is this equality. Then we can expand this again further to get 2 minus m x minus m plus 2 minus m xi. Then this is minus m x minus m minus 1. Then partial derivative of the norm of x. Again, we apply the result of the partial derivative of the norm of x in this place. That is xi norm of x. So what we get? We will obtain the that is 2 minus m norm of x minus m plus 2 minus m xi minus m norm of x minus m minus 2. Then we have an xi. Okay, so finally this is 2 minus m x minus m minus m 2 minus m xi square over x norm m plus 2. Okay, this is the result. Therefore, the gradient of v from the partial derivative of v with respect to xi, we know that the gradient of v is 2 minus m x over the norm of x to the power m. And the Laplacian of v is the sum I from 1 to m of the second order derivative of v with respect to xi. That is the sum of 2 minus m x minus m minus m 2 minus m xi square xi m plus 2. Okay, simplified this computation and observe that the sum of xi square is precisely the square of the norm of x. So you can obtain the final result, that is 0. So we have a function v. We have constructed a function v that is given here, given at the beginning of this page. We have this function v, whose Laplacian is 0, and whose gradient is a constant multiplying x over the norm of x to the power n. Okay, this is just what we want. We want to find the function. The gradient is x over the norm of x to n, and the Laplacian is 0. So we apply this v and our f in we substituting the f, the u, which our f, and the v, which this v will just construct to the green first identity. So we obtain the work. But to apply the green identity, we still need to compute the derivative, the directional derivative of v, which respect to the unit normal vector, which respect of this the boundary of the domain. So the boundary of our this domain is b1 minus b epsilon. We denote this by simply this. So the outward normal vector on the unit sphere is point outward, but it is point inward on the inner boundary. That is the boundary of b epsilon. The sphere of radius epsilon, it points inward because you want to point outward of the domain, so you need to point inward on the inner sphere. Therefore we know that the mu is minus x. This is the outward normal unit outward normal on the boundary of the inner sphere. Therefore, on this part of the boundary, the directional derivative of our function v equal the gradient of v inner product, which is nu. The gradient of v is 2 minus m x norm m, and the nu here, the normal vector is minus x over the norm of x. So we inner product which minus x the norm of x. So the result is m minus 2. The x norm m minus 1. Okay, the inner product of these 2x is the norm of x, the square of the norm of x, and cancel cancel the square of the norm, which the denominator we have x norm m minus 1. So this is m minus 2 epsilon m minus 1, because on the sphere of boundary, on the sphere of radius epsilon, the norm of x is precisely epsilon. Yeah, okay. So we get this result. So this is the preparation of our computation. Now we can conclude our computation. We have that 2 minus m epsilon x less than 1 x gradient of f xm dx. This is the b1 minus b epsilon. Our v inner product with our f, then dx. Okay, because v is just this function. V is just this function, and with the 2 minus m. Okay, so we have this equality. Okay, now for this equality, we apply the Green formula. The Green formula first the Green identity, that is gradient v gradient of f plus v plus f Laplacian v equal the integral over the boundary of f dvd new. Okay, this is the green first identity, but the Laplacian of our v here is 0. So this integral is just what we have on the left hand side of the green first the green identity. So we obtain that this just equal the boundary of this domain, removing the ball of radius epsilon from the unit ball. This is our integral domain. Then f multiplying the directional derivative of v. Okay. So, but f is 0. Our condition says that f is 0 on the outer boundary. So f is 0 here, and we also have of radius epsilon. This is of radius 1. Therefore, the boundary of this domain consists of two parts. The boundary is the union of two parts, and on the outer part, that is the unit sphere. Because f is 0 there, so this term vanishes. Okay, so we only have the sphere of radius epsilon part. But this directional derivative we just computed on the previous page. This partial derivative is computed in the last line of this page, which is n minus 2 epsilon n minus 1. Okay. So this is f n minus 2 epsilon n minus 1. Okay. But applying the mean value theorem, the mean value theorem says that for a continuous function, the integral of f over a surface will equal some point on the surface multiplying the area of the surface. We have this mean value property of integral. No matter you are definite integral on an interval or multiple integral over a connected region, or even surface integral, this always true. Okay, so applying this result to this computation, we know that this equals to some point. This point I denoted by x epsilon, multiplying the area of the sphere of radius epsilon. Then we also have the n minus 2 here. I forgot to write it. So we also have n minus 2 epsilon n minus 1. Okay. So the area of the sphere of radius epsilon is the area of the unit sphere we denoted by epsilon m, omega m. Omega m is the area of the unit sphere in Rm. So the area of the sphere of radius epsilon is the area of a unit sphere multiplying epsilon m minus 1. Okay, we have this result. Maybe we have not proved this, but the area of the surface, we have a definition. Using the definition, it is not difficult to get this result. Okay, so using this result, the epsilon n minus 1 can be cancelled. So we get the result n minus 2 f x epsilon. X epsilon is a point. X epsilon is a point on the sphere of radius epsilon. So when epsilon goes to 0, we are computing the limit at when epsilon goes to 0. So when epsilon goes to 0, x epsilon will goes to the center of the sphere. So this will converge to n minus 2 f0 as epsilon goes to 0 by the continuity of f. So 2 minus m multiplying the integral we are concerned will converge to n minus 2 multiplying the value of f at 0. So our limit, the limit we are required to compute is I. Okay, here. This is what we want to compute, the I. So I is just minus f0. Okay, because we multiplying 2 minus m to the integral in I, and computed the result and found that it converges to n minus 2 f0. So concerning the n minus 2, you will see that the limit is minus f0. So this complete the this question.